Swayam Prabha. Digital India. Educated India.
Good morning and welcome to this, the 27th lecture of the course Stochastic Hydrology. We have been discussing the frequency analysis, and specifically in the previous lecture we covered the frequency factors, that is frequency analysis by analytical methods. We discussed the frequency factors for normal distribution, for the Gumbel's extreme value type 1 distribution, that is EV1, which is also known as the Gumbel type 1 Gumbel's distribution, and the log Pearson type 3 distribution. If you recall, for the normal distribution, the standard normal deviate Z itself becomes the frequency factor, and we use the frequency factors to compute the magnitudes of the flows, if we are doing the frequency analysis for the flows corresponding to any given return period. So, if you recall, we wrote the expression as x t is equal to x bar plus k t into sigma, or if we are doing it for samples, we write k t into s. Now, k t is the frequency factor corresponding to a return period of t, capital T. So, this will depend on the return period that we are talking about, and t is also equal to 1 by p. All these are necessary for carrying out the frequency analysis, where p is probability that x is greater than or equal to x t. Now, all of these are the preliminaries of frequency analysis. So, we are interested in getting x t, which is the magnitude of the flow if we are doing it for flow frequency analysis, which is typically the case. Flood frequency analysis is what we carry out. So, this is the magnitude of the flood corresponding to a return period of t, and the return period of t is related to probability of exceedance by t is equal to 1 by p, and we are doing the analytical frequency analysis by using this expression x bar plus k t times s, where k t is the frequency factor. And we discussed the k t, which is a frequency factor corresponding to the normal distribution, which, as I said, is the normal standard normal deviate Z itself. And then for the Gumbel's extreme value type 1 distribution as well as log Pearson type 3 distribution, I have given you the formula for obtaining the k t, which is the frequency factor. We also discussed subsequently the probability plotting, that is, when we have the data, how do we check whether the particular data fits a given distribution or not. And we started with the discussion on plotting the data on probability papers, and specifically we started discussing the probability paper construction by mathematical method, that is by analytical method. And if you recall, we discussed the exponential distribution to demonstrate how we construct the probability paper. If I would like to reiterate here that essentially what we do in probability paper construction is that we are converting the nonlinear CDF into a linear form. So, the scales are adjusted on the paper such that the CDF plots as a straight line, and that is what we did in the case of exponential distribution. We could do that in exponential distribution because it is a kind of invertible distribution, in the sense that given the CDF we would be able to express x in terms of the CDF, whereas many other distributions, for many other distributions it is not readily possible for us to express x in terms of f of x given the analytical expression for f of x. In such situations, we fall recourse to the graphical method. What do we do in the graphical method? Let us say that you plot any CDF on an arithmetic paper. How does the CDF plot? It will typically plot as a nonlinear curve. Now, this nonlinear curve, we make it as a linear curve by adjusting the scales of the arithmetic paper, and this adjusted scale on the arithmetic paper will convert the arithmetic paper into a probability paper. We will start, we will demonstrate this procedure by the normal distribution. So, in the graphical distribution, for the normal distribution, let us say for the graphical construction is done by transforming the arithmetic scale to probability scale. So, that when you plot the CDF, you will obtain a straight line. This transformation technique now we will discuss through the normal distribution. For the normal distribution, we have the standard normal table, standard normal distribution table. We make use of that and then look at the f of z, capital F of z for various values of z. First, we plot f of z versus z on an arithmetic paper and see how it plots. So, these are the f of z values. Typically, if we use a table like this gives the area under the standard normal curve from 0 to that particular value of z. So, you add 0.5 to that by symmetry to get the complete area until this point, and similarly if you are looking at a z which is less than 0.5, you will deduct, you will use the area directly, and to get the probability on the other side, for that you will deduct this particular area from 1. So, all of these fundamentals of normal distribution we have studied earlier. So, typically this is how the table looks. These are available in any standard textbooks on probability and statistics. So, we have shown only a partial table here. So, for a given z, you can obtain f of z using this figure here. So, we use z and the associated z value. Let us say from -3 to +3, about 99.9% of the values of the probability is contained in that. So, we use typically from -3 to +3, and these are the associated z values. This z versus f of z we will plot first on the arithmetic paper and see how it plots. So, on the arithmetic paper, on the y axis I plot the z, on the x axis I plot the f of z. This is how it looks. So, -3 corresponding to 0, not exactly 0, but very nearly 0, and +3 corresponding to nearly 1. And this is a nonlinear curve, and at 0.5 it corresponds to 0, that is z is equal to 0 corresponding to f of z of 0.5. Normal distribution being symmetric distribution, we have a symmetric curve plotted on the arithmetic paper. What we will now want to do is, we want this relationship between f of z and z to plot as a straight line. So, what is it that we do? We convert this figure, we convert the scales in fact on f of z such that this figure plots as a straight line. How do we do that? We plot a straight line now. We take a straight line passing through z is equal to 0, f of z is equal to 0.5. We plot a straight line and then transform the associated coordinates of f of z from this curve to that straight line, that is all. Which means that essentially we are transforming the f of z scale here from the arithmetic scale to another scale which we call as probability scale, such that this CDF which is plotted as a non-linear curve will in fact plot as a straight line. So, the procedure is very simple. Once you plot the f of CDF, simply take a straight line which best represents that particular CDF and then transform the coordinates, transform the scale on the f of z to a probability scale such that all of these points are transferred to the straight line. We will see how it is done now. Let us say this was your plot on the arithmetic scale. So, this curve here shows the plot which is the same plot as is shown here. And we draw a straight line between -3 to +3 here on the z axis, passing through, and it passes, this straight line passes through 0 and 0.5 or 0.5 of f of z corresponding to a value of 0 here. Now, we start transforming the values on f of z. So, f of z for example 0.3 would have corresponded to this particular point, but we want this point to be on the straight line. So, we transfer this point to this and then project it upwards and call this as 0.3. So, essentially what we did is that we are saying 0.3 should not be here, but it should be here, and therefore, I take it to 0.3. Similarly, 0.2 I come and reach the curve, take it horizontally, reach this particular point and then say it is 0.2. Similarly, 0.1 and so on. On the other side, you take 0.8, reach the curve first, go left side and hit the straight line and project it upwards and 0.8. Look at this scale now 0.01, 0.05, 0.1, 0.2 etcetera, which are much different from the arithmetic scale. So, this is how we converted the arithmetic scale to a probabilistic scale. So, when you plot it on the probabilistic scale, the data which we have used will plot it as this particular straight line. Then we prepare a probability paper now, which means the probability scale will be this and the z axis is arithmetic scale. So, you can use to plot any data on the arithmetic scale, and the probability scale will be nonlinear as you can see. So, this is how it appears. The probability paper, normal probability paper will appear like this. These probability papers are commercially available. You can also get it from internet from various sources. What we have done is, this one is redrawn from the webull.com website, which provides the normal probability paper, as it indeed provides probability papers for Gumbel distribution and other distributions. Typically, in such papers, the x axis contains the probabilities in percentages. See, in this particular probability paper, I have shown probability of x being less than or equal to xm in percentage. So, 99% starting with 0.1%, and similar things are shown with 1 minus probability of x, that is in percentage 100 minus probability of x. So, probability x being greater than or equal to xm, here it is x being less than or equal to xm. So, you start with 1, go up to 99%. And the y axis here, as you can see, is an arithmetic scale. So, the x axis is probability scale, y axis is arithmetic scale. We use this probability papers and plot the data on the probability paper to check whether the given data follows normal distribution or not. What will happen if it follows normal distribution? It would follow this particular straight line, or the values will all be around this particular straight line. So, if you plot the data that you have on the normal probability paper and it plots as a normal distribution as a straight line on this particular probability paper, then you can reasonably assume if it plots nearly as a straight line, then it is a reasonable assumption that the data in fact comes from a population which follows normal distribution. So, the purpose of the probability paper is to check if the if a data set fits a particular distribution. Let us say you have exponential distribution probability paper that we discussed in the last lecture, and you have normal distribution probability paper. Similarly, you have typically Gumbel's distribution. In hydrology, mostly we use normal and Gumbel distribution. So, once you have the probability papers, you fit the data on that particular paper, and if the data fits as a straight line or it fits nearly as a straight line, then you can assume that the data that you have as a sample, the sample data in fact is drawn from that particular distribution, normal or Gumbel or whatever. Now, once you plot this, you can use that, let us say that it plots as a straight line on the normal distribution. You can use that for interpolation, extrapolation, and also for comparison purposes. Another normal distribution, how does it compare with the particular data that you have, and so on. So, the probability paper is very useful, especially for obtaining interpolated data, in the sense that let us say that you want to talk about a flow duration, flow magnitude of 15-year return period, which from the data it is not directly possible for you to get. Then once you plot it as a straight line on the normal probability paper, for example, you will be able to get the magnitude corresponding to 15-year flow data. That is the interpolation. You can also use it for extrapolation. Let us say your data range was only up to let us say a return period of 10 years, 15 years, etc. You can obtain it straight away, but you are interested in getting a return period, a magnitude of flow corresponding to a return period of 200 years, 300 years, which are typically the case in most hydrologic designs. Then you can use this procedure for extrapolation also. That is, once you have the straight line, you can also extrapolate and then look at return periods which are which far exceed what you can get from the sample data itself. And that is what, if you recall, we do in frequency analysis. However, I must alert you here that extrapolation must be done very carefully, because in extrapolation essentially what we are doing, we are looking at the extreme values. Let us say 200-year return period, 300-year return period, etc. These are typically the extreme values which are located on the tails of the distribution, and tails of the distribution are very sensitive to change in probabilities. I will demonstrate when I explain the example there what I mean by that. So, whenever you are using the probability paper for extrapolation, you must be reasonably sure that the data fits that particular distribution. If you have any doubt on, especially on the extreme values departing further away from the straight line, then you have to be careful in doing the extrapolation, especially because you use the extrapolation for flood frequency analysis, where the difference between a 200-year return period flow or flood and the 300-year return period flood may be significant, and therefore, the method that you use to estimate these return period floods must be accurate. Otherwise, it may lead to costly decisions in terms of the economies, economic investments and so on, or it may lead to so conservative decisions that the decisions may be wrong, and therefore, achieving the right value of the magnitude that arises out of the probability papers must be a major concern, especially when you are dealing with the extreme values. We will now see what we call as the plotting position. Look at the probability papers here. What I said is that you plot the data on the probability paper. Now, to plot the data on the probability paper, first you must have the data magnitude, which you can plot it on the y axis, but you also need the corresponding probability values, probability of x being less than or equal to x m or x being greater than or equal to x m and so on. Now, these are obtained from probability plotting positions. The basis for this is that you have a small sample of data, or even if it is large, comparatively large, it is only a sample. Now, from this sample you want to estimate the probabilities of exceedance, that is probability of x being greater than or equal to x, a given value of x, or probability of x being less than a particular value of x, and so on. This we estimate by using the probability plotting positions. We call it as plotting position because they are not actual probabilities. See, there is a sample that you have, let us say of the observed data, and this observed data you are now examining whether it is in fact drawn from a particular from a population belonging to a particular distribution. And therefore, we use this not as actual probabilities, but as plotting positions, so that we can plot it on a probability paper or even on a arithmetic paper. So, typically we are saying probability of x being greater than or equal to x m is estimated by such and such a formula. So, we have is a number of formulae for plotting position, these are called as plotting position formulae. So, the plotting position is a simple empirical technique. There is not a rigorous analytical basis for the plotting position, and what we do in this is that we use the fact that there is a relationship between the magnitude of an event versus its probability of exceedance. This exists, and this relationship is what we are capturing or what we are depicting through the plotting position. And we say the plotting position actually refers to that particular probability value, although it is not exactly a probability, it just refers to that particular probability value assigned to each of the data to be plotted, which means you have in the sample you have several data points associated with each of the data point. We provide a probability plotting position and then say that this plotting position in fact refers to the probability of exceedance of that particular value. In hydrology, we use several of the plotting positions typically, and I will go through some of the empirical methods which provide the plotting positions. Typically, you have let us say n number of values, let us say 50 years of monthly data values, which means 600 values. All your decisions must be based on what you have observed on the field. So, this is the observed data. So, we are basing all our decisions on the observed data. What we do is that we arrange this sequence in decreasing order. So, from the highest value first to the lowest value last, we arrange it in a decreasing value, and we assign an order or a rank to each of the values, starting with the highest value taking number 1 and the last value taking rank of n, if you have n values. So, if you have n number of values and m is the rank of a particular value, then the exceedance probability of the mth largest value is obtained by various plotting position formulae. That is all. That means, we have assigned to each of the data point a rank m, and n is the total number of values. So, associated with this m, we estimate the probability of exceedance using both m and n. And the return period of the event of a particular event is typically calculated by 1 over p, where p is the probability of exceedance. Once you get the plotting position, we plot the magnitude of event versus the exceedance probability p itself, or typically 1 minus p, or even the return period. So, the plotting position is used to plot either p or 1 minus p or the return period, which are all functions of p. So, we typically plot data versus p or data versus 1 minus p, which is probability of non-exceedance, and data versus the return period. So, typically these are what we generally use in frequency analysis. Now, there are, as I said, several formulae that have been proposed in hydrological literature for plotting positions. We will just go through them one by one, and then we will use one of the methods to see how we estimate the plotting positions, and then also see how we plot using the plotting positions on the normal probability paper. Similar procedure can be used for any other distribution. So, the California method says probability, this is a plotting position, is simply given by m divided by n, where m is the rank that we have provided to the particular data point. So, x m is that particular data point and m is the rank associated with that, n is the total number of values. Now, this has a limitation that it produces a probability of 100% for m is equal to n. So, the moment we assign a probability of 100%, it means that we are sure that we have in our data captures all possible values, and therefore, we are assigning a probability of 100% for a particular data point. This becomes a limitation, because we cannot be always 100% certain that the data sample that we have is in fact representative of the total population, and therefore, this becomes a limitation, although it is a very simple way of assigning probabilities. So, this is how it started the plotting position, simply take m by n, and a modification was suggested to the California method, where we do not take m by n, but we take m minus 1 by n. Now, the moment we put m minus 1 by n, we have taken care of the limitation arising out of assigning 100% probability. However, we have introduced another limitation now. M is equal to 1, the probability is 0. The moment m is equal to 1, it becomes 0. Now, this is not a limitation. The first one, formula does not produce 100% probability. This is not a limitation. However, the second one becomes a limitation. This is a limitation. That is, when m is equal to 1, you get a probability of 0. Now, probability of 0 again indicates that you have captured all the lower extreme values, and therefore, you are confident that a probability of 0 does exist, and that becomes a limitation, because we can never be sure that the sample is in fact a complete representation of the population, especially when we are talking about flow probabilities, flood probabilities and so on in hydrology. Then we have the Hazen's formula, which does a compromise again between just taking m by n and taking m minus 1 by n. It takes m minus 0.5 by n. Then we have the Chagodet's formula, where it takes m minus 0.3 by n plus 0.4. As I said, these are all empirical methods. They have done several tests on these and then propose these particular formulae. Then you have the Weibull's formula, which is the most commonly used formula in hydrology. In fact, the moment you want to use a plotting position, the first thing that comes to your mind is the Weibull's formula. This is most commonly used for the reasons that I mentioned presently. So, if you have n values which are all distributed uniformly, let us say you have the data sample, and then if this data is uniformly distributed, then between 0 and 100% probability, that is what we are assuming. That means, you have the data samples, and then between 0 and 100% probability, these data are uniformly distributed. That means, there is no probability band which has more number of data than any other probability band. That is assumption there. Then you can get probability of x being greater than or equal to x m is m divided by n plus 1. That is, you are leaving out 0, you are leaving out 1 on the other extreme, and then remaining n minus 1 values, n minus 1 class intervals contain these data in a uniform manner, in a uniformly distributed manner. So, you will have n plus 1 class intervals, that is n minus 1 between the data points and 1 at the other one extreme containing 0, another at the another extreme containing 1. So, that is how you get n minus 1 plus 2, which is n plus 1. and the probability of x being greater than or equal to x m is then given by m divided by n plus 1. So, this indicates a return period t 1 year longer than the period of record for the largest value. So, you have the largest value in the data and then you have the largest value should have corresponded to m divided by n, but now it corresponds to m divided by n plus 1. This has several advantages. First of all, it does not produce a probability of 0 because m starts with 1, and it does not produce a probability of 100% because at m is equal to n you still have n divided by n plus 1, and therefore, the Weibull's formula is most commonly used in hydrologic analysis. Now, we discussed a few of them, but there are several others plotting formula. Most of the plotting formulae may be expressed by this simple expression m minus b divided by n plus 1 minus 2 b, where b is a parameter. So, this gives a general formula for plotting positions. For example, you take Hazen's formula, b is equal to 0.5. So, m minus 0.5 divided by n plus 1 minus 0.5 into 2, 2 into 0.5, which is this goes. So, m minus 0.5 by n, that is what leads to Hazen's formula. Then b is equal to 0.5 again for Chagouday's formula, and for Weibull's formula you put b is equal to 0, it is m divided by n plus 1 minus 0. So, m divided by n plus 1. Similarly, b is equal to 3.8 for Bloom's formula, and b is equal to 1 by 3 for Tukey's formula, etc. This 0.5 does not exist. Like this, you can generate several formulae by using different values of b, and some of them are proposed like this. Now, there is one study which was done long ago in 1978. He uses, that is Conan studied the various available plotting position methods based on unbiasedness, which of these are unbiased and which of them also lead to minimum variance. And he observes that if a large number of equally sized samples are plotted, the average of the plotted points for each value of m lie on the theoretical distribution line. So, this must be ensured by your plotting position. Then the minimum variance plotting minimizes the variance of the plotted points about the theoretical line. So, you have the theoretical line and then you have plotted the data using the plotting position. Then your plotting position must be such that among all the plotting positions, it must lead to a minimum variance of plotting. That means, the variance if you calculate between the observed and the theoretical values, that variance must be minimum. So, this is what we generally use as criteria for choosing the plotting position, but as a first cut solution to most of the hydrologic problems, you generally use the Weibull's plotting position. For normally distributed data, the Bloom's plotting position is commonly used, and for extreme value type 1 distribution, we use the Gringorten formula, which b is equal to 0.44. Now, whether you use one plotting position or the other, as far as the center of the distribution is concerned, there is not too much of a difference between the plotting positions provided by these various methods. However, when we look at the extreme values either on the high extreme or on the low extreme, the plotting positions can be quite different from one plotting position to another plotting position. And therefore, when you are dealing with extreme values, you must be specifically attentive to which type of plotting positions that which of these several plotting position formulae that are available, which among them you would like to use. Now, this comes from the judgment of after looking at the plots of the data on the probability papers. You may see that at the central point of the plot, in the central point of the plot, most of the data are agreeing with the straight line, but as you go towards the extremes, the data may be far away from the theoretical straight line. If they are indeed far away from the straight line, and if you are using this particular procedure for extreme values, then you must be careful. You should not use such distributions. Now, from the Gumbel study early in 1950s, we have the following criteria to be met by a good plotting position relationship. First of all, the plotting position must be such that all observations can be plotted. That is how you have m as well as n. So, you have n number of values and m goes from 1 to n, and all of these must contain both m and n. So, that you are able to plot all the observed values. Then the plotting position should lie between the observed frequencies of m minus 1 by n and m by n. That is, this is the probabilities. So, as I said, you leave out 0% and 100%. So, it must lie between m minus 1 by n and m by n. The return period of a value equal to or greater than the largest observation and the return period of a value equal to or smaller than the smallest observation should converge to n. Now, this is an important and interesting property of the plotting positions. What do we mean by that? Return period is given by t is equal to 1 by p. So, you take the largest observation in the data that you have. So, the return period of a value equal to or greater than the largest observation. So, get the return period corresponding to that, and the return period of a value equal to or smaller than the smallest value, both these must converge to n. Now, that is one of the requirements of a good plotting position relationship. Then the observations should be equally spaced on the frequency scale. What do we mean by that? That you are saying that this data should map on to that particular distribution, and the distribution of the data themselves in various probability bands must be equal. So, that is what we mean by the observation should be equally spaced on the frequency scale. And the plotting position should be analytically simple and easy to use, which is obvious, because we want to finally recommend these to the field engineers who are in hydrologic designs. So, this must be simple. So, these are some of the criteria that Gumbel has brought out for a good plotting position formula. Let us look at the Weibel's plotting formula. Okay. Weibel's plotting formula, plotting position formula is given by probability of x being greater than or equal to x m is equal to m divided by n plus 1. M is the rank when we arrange it in descending order, and n is the total number of values. Now, the first condition is that all the observations must be, we must be able to plot. So, all the observations can be plotted, since the plotting positions range from 1 divided by n plus 1 for the highest value to n divided by n plus 1. So, this is greater than 0 and this is less than 1, and therefore, you can plot all the values. The relationship lies between m minus 1 by n and m by n, because we are talking about m divided by n plus 1 for all values of m and n, and therefore, the second criteria is satisfied. The return period of the largest value is n plus 1 divided by 1, that is, we are talking about m divided by n plus 1. So, it will be the largest value will have a rank of 1 and the probability associated that will be 1 divided by n plus 1. This has to be 1 divided by n plus 1, I am sorry here, 1 divided by n plus 1, and for the smallest one, so what happens, okay, I am sorry, this is not, we are talking about the return period. So, return period, as you know, is 1 divided by p. Let me explain that. So, return period is 1 by p. So, the return period corresponds to n plus 1 divided by 1. So, if I take out all of this, okay, I will explain this again. So, we are now talking about the return periods, not the probabilities. So, return period is 1 by p. So, 1 by p will be n plus 1 by n, because your p is 1 by n plus 1, and therefore, the return period is n plus 1 by. So, as n increases, which approaches n as n tends to infinity. So, this will be n plus 1 by 1 will be almost equal to n as n approaches infinity. Similarly, the return period for the smallest value, that means, we are looking at the last value, and the probability is n divided by n plus 1. Therefore, the return period will be n plus 1 by n, which approaches 1 as n tends to infinity. As n tends to infinity, this becomes 1, and that is why that is how it satisfies the condition 3 of Gumbel's conditions. Then the fourth condition is the difference between the plotting position of the m plus 1 and mth value is 1 divided by n plus 1 for all values of m and n. What is the fourth condition of Gumbel's? This is the observation should be equally spaced on the frequency scale. Now, that is what we are saying here. The difference between the plotting position of the m plus 1th and the mth value is 1 divided by n plus 1, which remains the same for all values of m and n. That means, the frequency remains the same across different plotting positions, and of course, the formula is simple and easy to use. Therefore, the Weibel's formula meets all the requirements as proposed by Gumbel in 1958, and therefore, the Weibel's formula is most commonly used in hydrologic analysis. Okay, we will take a simple example now. We are looking at the maximum flow of a river for 60 years, and we will look at the probability plotting analysis. We use the Hazen's formula. I use the Hazen's formula for convenience here, because we use MATLAB, and in MATLAB Hazen's formula is what is used for normal distribution. However, you can use Weibel's or any of the other earlier plotting position formulas that I have mentioned. And then we will see whether the given data in fact can be approximated as belonging to normal distribution. Now, this is the data from 1950 to 2009. So, 59 plus 1, that is 60 years of data. These are the annual maximum discharges in million cubic meters. So, these are the values. This is year and this is the value. What we do is that we arrange this data in decreasing order. That means, the highest value first and the lowest value last. So, first the data is arranged in descending order, and we assign ranks to each of the data. That means, rank number 1 to the highest value, rank number 2 to the next highest value, etcetera, rank number n to the last value. And then we obtain the probability x being greater than or equal to x m. This is the Hazen's formula, m minus 0.5 divided by n, where m is the rank corresponding to that particular value and n is the total number of values. And the maximum annual discharge versus the return period is plotted on a normal probability paper. So, this is what we get from the plotting position, and then we have the given value of the data, that is the maximum annual discharge, and the return period we can plot. Return period is 1 by p, or we can also plot the probability of exceedance or probability of non-exceedance. We can use the probability paper for plotting any of this. So, we take, let us say we pick up the maximum value 3, 2, 5, 6 and assign rank number 1, next value assign rank number 2, etcetera, like this. So, we assign up to ranks 60 in in the data. So, it goes from ranks 1 to 60. Once we get the ranks, we can get the plotting position. So, we get plotting position x being greater than or equal to x m using this formula. So, these are the plotting positions. Okay. And then we use the normal probability paper, which I had indicated earlier. In this case, we use the normal probability paper. Earlier, I had indicated the probability scales on the x axis. This differs and it is just based on your convenience. You can use either the x axis to indicate your data or x axis to indicate the probabilities. Many commercially available probability papers will use x as x axis as the probabilities, but in this particular case I am using the MATLAB program. Though the MATLAB syntax is simply non plot given data. So, data is a vector, you simply give non plot and it uses the Hazen's formula for plotting position and then generates this probability paper, plot on the probability paper. So, here we have shown probability of x being less than or equal to x m and here we have shown probability of x being greater than or equal to x m. That is what is obtained from this table here. So, probability of x being greater than or equal to x m is what is shown here. So, for example, you have a probability of 0.008. So, you get somewhere here 0.008 and that corresponds to this value. So, on both these axes, vertical axis, you can get the associated probabilities. The theoretical line in this case is shown by the red line here. That is, this is the best fit line, straight line for that is if this data set were to follow a normal distribution theoretically, then all of these points would have come on this particular straight line. But there are some departures, some of the data are departing from the straight line. As you can see, in the central region of the plot, most of the data are very close to the straight line. As you go near the extremes, for example, this point, these points here, etc., as you go near the extremes, the departures are quite significant. So, if you are interested in the central region, we can reasonably assume that this follows a normal distribution. And typically, when we want to use normal distribution, we are generally interested in the central region. So, unless you are looking at extremes of let us say 1 in 1000 year return period, 1 in 500 year return period flows and so on, unless you are looking at those extremes, you can reasonably use the normal distribution for this particular data. Now, let us say you look at difference between 10-year return period and 100-year return period. What does 10-year return period correspond to? Let us say you are looking at t is equal to 10 years. So, t is equal to 10 years will correspond to the probability is 1 by 10, which is 0.1, and t is equal to 100 may correspond to 1 by 10, 1 by 100, which is 0.01. So, you may be looking at in terms of percentage, you may be looking at 10% and 1%, the difference between 10% and 1%. So, this may come to be let us say your this is not in percentage. So, you are actually looking at 0.1 and 0.01. So, you are looking at the difference between 0.01 and 0.1. So, this may be may appear to be small compared to the other scales here, but the values that you get may be significantly different. So, on the graph you may be tempted to say that there is not too much of a difference, therefore, I can use this graph also for obtaining 100-year return period, 200-year return period and so on, because you do not see too much of a difference in the graph itself here. However, because you must remember that this is a highly nonlinear scale and therefore, the values that you get may be significantly different and therefore, you must be alert to the situation that near the extremes the difference is, if they are significant, the values are significantly departing from the theoretical straight line, then you must be alert to using these for extrapolation purposes near the extreme values. That is the point that I want to drive. So, the plotting position, when the probability plots of hydrologic data are made, typically you may have some extreme values which may be far away from the straight lines. In this particular case, let us say this value or this value etcetera, they may be far away from the straight lines and in between we may get a value here. Let us say that some values may for example, I may get a value here, something like this, or some value somewhere here. Now, these are quite far away from the theoretical straight line compared to most other values. Most other values you may say that the departure is only very small random deviation from this straight line and therefore, it can be accepted. Whereas, there may be some values which are far away from the theoretical line. These are called as the outliers. That means, in the data that you have observed, let us say that all of this data were somewhere around this region, but one or two values may be far away from this data. These are called as the outliers. Identification of outliers from a given data is itself an exercise. That means, given the data, do we call this as an outlier or do we include it in the analysis? And you may not have just one outlier like that, you may have a series of outliers. Let us say some outlier may lie here, somewhere here, and some other value may lie here, etcetera. Whereas, most of the other data are all around the line. Now, in that case, first of all, these are outliers. In such a situation, first identification of the outliers itself is a problem and then how do we make use of the outliers in our analysis is another problem. I will not be discussing this in this particular course. However, you keep in mind that when you get the data here like this and then some of the points are far away, how do we treat them is a different topic by itself. You must remember that you should not simply ignore the outliers depending on the type of analysis that the type of use of this analysis that you would like to make. You may have to consider the outliers in different ways. What I mean by that is these outliers have actually happened, have actually occurred in the history and therefore, they are telling you some story, they are giving you some information and this information cannot be simply ignored. So, you must always be alert to the situation that the outliers are providing some information which if we ignore, perhaps we may be making too much of an approximation. So, the separate treatment a separate treatment is required for the outliers. So, we will say here. Now, there is a good literature available for treatment of outliers and anyone who is interested in taking these discussions forward can refer to many of the most of the literature related with outliers and this is classical literature now right from 1960s. Now, if you have enough historical information, that means that the data is quite large, data is quite reliable and data has not undergone any changes in terms of time wise homogeneity etcetera, then you can still treat the outliers in a reasonable manner. So, in today's class essentially what we did is we started with probability plotting and continued the discussion on the probability papers. In the last lecture, we had discussed the mathematical way of obtaining the probability papers. Today, we discuss the graphical procedure of obtaining the probability paper, dealing essentially with the normal distribution. What we do is that we convert the arithmetic scale into a probability scale, so that the probability distribution, the CDF, plots as a straight line on the probability paper, and that is how we obtained the normal probability paper. Similarly, you can also obtain Gumbel's probability paper, log Pearson type 3 probability paper, and so on. Then to use the probability papers, we need a plotting position. The plotting position, we have introduced several formulae, and typically we use the Weibull's formula for most of the hydrologic procedure, hydrologic analysis, which is given by m divided by n plus 1, where m is the rank of that particular data when we arrange the data in a descending order. Why do we use the probability papers? The probability papers typically are used as a first cut approximation or first cut judgment on whether a given data set that you have in fact fits that probability paper probability distribution or not. If the data with the associated plotting positions plots as a straight line or nearly as a straight line, then you are reasonably sure that you can use that data sample as belonging to that, as belonging to a particular population which follows that particular distribution, say normal distribution or Gumbel distribution, and so on. You must also be careful in extrapolating the data from the distributions that you so obtain. Let us say that most of the data in the central region follow the particular straight line very closely, but at the extremes you have departures, you have significant departures. Then you should be wary of doing extrapolations in the extreme regions. So, we will continue this discussion and introduce analytical procedures for testing whether a particular data set fits a given distribution or not. That is, we have the data set. What we did through probability papers is that we constructed the probability papers and then plotted the data set and then saw whether it plots as a straight line, and then made a conclusion or judgment on whether it fits that particular distribution or not. Now, we look at analytical procedures. What do we do in the analytical procedures? If you want to test whether it fits a particular distribution, say normal distribution, theoretical distribution, we get the expected frequencies from that particular theoretical distribution, and we compare it with the observed frequencies arising out of the data, and then look at how closely, in some statistical sense, how closely the observed frequencies match the expected frequencies. And this is what we discuss in the next lecture. So, thank you for your attention. We will meet again in the next lecture.